Okay, so up here, because of the keyword compounding, what happened? Okay, because of the keyword compounding continuously, you'd use PERT. So you do your $200 e raised to the 0.08 times 10, which after 10 years, we had $445.11, right? $445.11. And, you know, that's not that much, but it's better than zero if you had your money stuffed under your mattress instead of gaining interest. Okay, on this one, the compounding bi-monthly, we can't use PERT. We'd use that one formula. So it's still 200. 1 plus R over N. So our rate was 0.08. Our N is the number of times in a year it compounds. So that would be a 24 raised to the NT, 24 times 10. So then you would go ahead and calculate that, and you got 444.52. So now I want to remind you of how it's interesting that we were getting interest all the time right here at every given second. Right here we only got it 24 times in a year, yet it's only a teeny tiny difference, right? Like only within $1-ish. So everybody, why is that? Because once again, we talked about what happens with an exponential at a certain point, right? Kind of can't make that big of a difference, you know? Okay, cool. Hey, I want you to do these two. So this is what we learned last time. We use the one-to-one property to write both sides as the same base so that we can easily solve for x. So yes, in your notes, do this one. So you would rewrite these as the same base. What base would you, we need at base 3. 3 to the what power? Good. You'd say 3 is 27, negative flipped it over the fraction. So then now because we have the same base, we can now easily say that x must equal negative 3. Okay, sweet. Did you all get it right? Okay, let's do this one. So we have 1/3 raised to the x plus 3. That needs to equal 1/3. We need 9 to be rewritten as base 1/3. Negative. Now the final answer. Negative 2. Think about why that works. If we had a 3 to the negative 2 on bottom, it would flip up to the top, making it positive 9. Okay, good. So then from there, we would say our true statement must be x plus 3 equals negative 2. Therefore, x must equal negative 5. You could have also done this as, you could have said, I'm going to rewrite this as base 3 to the negative 1. So 3 to the negative 1 raised to the x plus 3 equals 3 squared. And then we could say, okay, so my true statement would be negative 1 times all that stuff equals 2. Negative 1 times x plus 3 equals 2. So then you would get x plus 3 equals negative 2. Therefore, x equals negative 5. Whatever floats your boat. Hey, let's begin the lesson. You should be taking some notes. So last time we learned how to graph an exponential, we were doing basics of exponentials. Now we're going to learn basics of logarithms, and they do have a lot to do with exponentials. So we know that an exponential function such as y is equal to base 2 raised to the x power, no matter what we plug in for x, if it's a negative, any negative number, it just flips it over a fraction, making it 2 to some power. So it's just going to get smaller and smaller and approach 0. It's never going to become 0. So with our exponential functions, we had this horizontal asymptote at y equals 0 here. And it just got closer and closer. We have a table of values here. Just look, because you guys get the picture here. If I plug in negative 3, I have an 8. And then if I plug in negative 2, I get a 4th. Negative 1, I get a half. Over 0, up 1. Plug in 1, we get 2. Plug in 2, we get 4, and so on. There's my xy points. Now, can anyone remember, if I said to you, find the inverse of those points, how would we find them? Flip them. We just switch xy points. So right here is an example. This red function is an inverse of these points. Well, fun fact for you. That is a logarithmic equation. So right here, this red function I've drawn is a logarithmic graph. So logarithms and exponentials are inverses of each other. So I want to point something out to you. If I switch these, that would be over 1/8 down 3. So look, over barely any down 3. Then over 1/4 down 2 units. Over 1/2 down 1. Over 1 up 0. See, I'm just switching them. Over 2 up 1. Over 4 up 2. And there's my logarithmic equation. Now think about it. The further we go right here, won't it just get closer and closer? Won't our x's just get closer and closer to 0? So wouldn't that mean that this must be a vertical asymptote at x equals 0? Yeah. That is true. That will happen. Okay, good. Sweet. So we just learned that a logarithmic function is the inverse of an exponential, and it's true to say also an exponential function is the inverse of a logarithmic function. So right here's where you'll want to start writing down. So if we have, this will be the form of a logarithmic equation, and you have to really understand how it's written properly and not be confused. So this is the function, y is equal to, this is read like this, log to the base a. This is like written smaller, it's like down here a little like sub, like a little small thing. So this is read log to the base a of x. Now of x, that's trapped inside the parentheses, like log to the base a of x. Does everybody see what I'm saying? Okay, cool. Now this is true if and only if. So IFF is a mathematical if. It's just saying if and only if base a to the y power equals x. So this is an exponential function. Base a to the y power equals x. Now this kind of feels weird because they really, since they're inverses, shouldn't our step be switch x and y? So really, we're really essentially looking at this. A to the x equals y. Because inverses need to be switched to x and y. So now we have this exponential function. Y equals base a raised to the x power. So you have to be able to switch from logarithmic form to exponential form and back and forth between the both. A lot of teachers will just have you memorize it. I'm going to just show you how to use algebra. We know inverses undo each other. Addition undoes subtraction. Division undoes multiplication, right? Exponentials and logs undo each other. So let me just show you how to switch back and forth using algebra instead, because then you don't ever have to memorize anything. So if I said to you, rewrite this, y is equal to log to the base a of x, rewrite that as an exponential function. So we would be finding the inverse essentially. So we would first switch x and y. So we would have x is equal to log to the base a of y. Now remember, after that, we solve for y. So we need to get y alone. It's trapped inside log to the base a. So I just told you that exponentials and logs undo each other. So log to the base a, the inverse of that is base a. So we would base a both sides of the equation. So now over here we have base a raised to the x power equals base a and log to the base a cancel out equals y. Sweet. So now we've written it in exponential form. It is awesome. Thank you. I appreciate that. So let's go backwards. I'm going to now come right here and say, okay, so if we have a to the x power, so y equals a to the x power, and I said write it in logarithmic form, I'm telling you to write it as an inverse. Find the logarithmic form. That would be the inverse. We would switch x and y. So we have x is equal to a to the y. Now you need to solve for y. But base a is raised to the y power. We can't drop down y without undoing base a. So we would take the inverse of base a, which is log base a. Now this is log base a, like a lot of people will think that this is an exponent like it was over here, but it's not. It's essentially this. I just can't squish it in there good enough. We're actually doing this. Log base a of a to the y. Does that make sense? We're taking log to the base a and then it eats that. So log base a both sides. We have to do it equally. So then over here on this side, we would have log to the base a of x, because it eats it, which equals log base a and base a cancel out equals y. And we've now put it in logarithmic form. Okay, so we will do that. We'll practice that more, okay? So, this is putting it into perspective for you. So we're not solving anything. We're literally taking a true statement and switching it to its exponential true statement. So everybody, we have log to the base 3 of 9 equals 2. So if I said to you, rewrite that in exponential form, you would need to undo log base 3. So we would base 3 both sides. Now look what happens. Log base 3 and base 3 cancel out, so 9 equals 3 squared. Isn't that a true statement? Yay, it is true. So that's good to go. Okay, let's look at this one. If I said rewrite 5 to the third, that's an exponential, equals 125, which is a true statement. I want it in logarithmic. It's logarithmic but equal form. You'd say, I need to undo base 5. I'm going to log base 5 both sides. So now on this side, log base 5 and base 5 would cancel out. So you would have 3 is equal to log to the base 5 of 125. And that is a equivalent statement. So just algebra. Sweet. Okay, so now we're going to evaluate these. So it says, what is log to the base 2 of 32? We've got to be able to do this by hand because most of our calculators cannot do base 2s. Your calculator only has a log button, not log to the base 2. Even if you can do it by your calculator, you're not allowed to touch your calculator. So evaluate log to the base 2 of 32. So because we don't know how to do this really without a calculator, let's rewrite it as an exponential and solve that way since we know how to solve exponentials. So we don't know what this is equal to, so I just go off to the side and say this. Okay, log to the base 2 of 32, we don't know what it's equal to, so I'm going to set it equal to x. I'm going to rewrite it in its exponential form. So I'm going to base 2 both sides. Base 2 and log to the base 2 cancel out. So now my true statement is 32 is equal to 2 to the what power? Yep, 2 to the x, so now we can solve. 2 to the what power equals 32? Well, do what we just did, everybody. 2 to the 5th power equals 2 to the x. So x equals 5, right? So log the base 2 of 32 will equal 5. So I'm going to do this one the same way. I'm going to rewrite this as an exponential so I can evaluate it. So we would go off to the side and say, so log to the base 3 of 1 equals we don't know. I'm going to rewrite it as an exponential, so I would base 3 both sides. Base 3 log to the base 3 cancels out. So what true statement? 3 to what power is going to equal us a 1? 3 to the what power equals 1? 0! Way to remember, you two. So log to the base 3 of 1 equals 0 then. Can you do these two by yourself? Okay, go for it. Okay, what did you get for the first one? Log to the base 4 of 2 equals 1/2. Log to the base 10 of 1 over 100 equals -2. Do we need to go over either of those? Both of those? Yes. Yeah, of course. So we would go off to the side and say our true statement is log to the base 4 of 2 equals x, base 4 both sides. So then we have 2 equals 4 to the x power. So then you'd have to say, like I heard him explain to his group, 4 to the 1/2 power equals 2 because we need the square root of 4. So 1/2 would be the square root. So yes, x must equal 1/2. Does that make sense? No, this would make it a true statement, right? 2 equals 4 to the 1/2. Isn't that a true statement? Okay. All right, are you sure that no one wants me to go over the second one? We can. Okay, so we would say log the base 10 of 1 over 100 equals x. We'd base 10 both sides to rewrite it as an exponential. So our true statement is 1 over 100 equals 10 to the what power? So write them as the same base. So isn't this equivalent to base 10 to the -2 power equals 10 to the x? Therefore, x must equal -2. Okay, awesome. Okay, now here is where you will definitely want to start writing down. These are basic properties of logs. And fun fact for you, a couple years ago, the calculus teacher came to me and she was like, seriously, it's so frustrating because my calculus students do not know what these simplify to be. And so I made sure to make it a huge goal to make sure you guys are good to go. Because when you know, once you learn these properties, within a half a second, you should know the answer to these. That quick. Okay, so our first property here. If we have log to any base of 1, log to any base of 1 will always equal 0. So log to the base 5 of 1 equals 0, log to the base 10 of 1 equals 0, log to the base smiley face of 1 equals 0. Now, why is that? Okay, why does that property work? You don't necessarily need to write down why, just think about why. So if I base a both sides, then I would have a to the 0 equals 1. Isn't it true no matter what I put in for a, that it's going to equal 1? So that's why no matter what, log to the base a of 1 equals 0. Okay, next one. Log to the base a of a will always simplify out to be 1. Here's why. So if I base a both sides, then my true statement would be a to the first always is going to equal a, isn't it? So here's a better way to think about it. Honestly, like I don't even think about that. All I do is go like this. Isn't it a log and an exponential? They undo each other. So this is really a to the first, isn't it? Log of base a and base a cancel out. So 1. That's why it simplifies to be 1. Okay, right here. So that's the same idea here. Log of the base a of a raised to the x will always simplify to be x. And honestly, it's just because think about algebra. Log of base a and base a cancel out, so it simplifies to be x. That's what inverses do. So then if we have base a raised to the log of base a, it's going to simplify to be x every time because those undo each other. All right. So now this is the same property we use for the one-to-one property of solving exponentials. So if I have 3 to the x equals 3 to the second power, because we have the same base, we can just say x equals 2, right? So this is what this is saying. If you have log to the base a of x, and you also have a log to the base a of y, because they're both log to the base a, you can then just say, well, x must equal y. Same idea. Okay, here we go. So we're going to do these within 30 seconds. No, a half a second. That's how quick. So what's log to the base 4 of 1 going to simplify to be every time? 0. Any log to the base of 1 will always equal 0. Okay, let's look right here. Log to the base 3 of 3 squared will simplify to be 2 because those undo each other. That quick. So base 6 raised to the log base 6 of 20 will simplify to be 20. You're awesome because base 6 and log to the base 6 cancel out. Okay, let's look here. Log to the base 1/4 of 1, 0. Once again, anything of any log to any base of 1 always equals 0. Good. Log to the root 7 of root 7. Yeah, it simplifies to be 1. How did I think of that so quickly? Or how did you? This is to the first power essentially, right? Those undo each other. Okay, log smiley face raised to the log smiley face of heart. Heart. You guys got it. Okay, cool. Now here's solving very, very simple log. Because they have the same base, can't we just say that x must equal 12? Sweet, that's right. Hey, look, log to the blank of that, log to the blank of that. Well, they're the same blank, aren't they? So our true statement must be 2x plus 1 equals x. Solve for x, so I'd subtract 2. What was wrong with me just now? So 1 equals, yeah, seriously. So 1 is equal to negative x, therefore x must equal negative 1, right? Okay, true. Here's a fun fact for you. What do you think this is? No? So I wanted somebody to just say 1, because then I'd remind you. Because that's great. That's what a lot of people would think. Because in math, a lot of times, if nothing's there, it's a 1, right? But fun reminder. So if I was to rewrite log to the base 1 as an exponential, wouldn't it be 1 to the x? is 1 to the x even exponential? No, it's linear, because no matter what you plug in, it's 1. So that was a good, that's what I wanted you to say. So anyways, it's actually secretly base 10. If there's nothing there, it's actually base 10. It goes without being said. Just like with a square root, it secretly has a 2 there, even though it's just something you have to memorize. Okay, cool. Let's do this one right here. Log to the base 4 of x squared minus 6, log to the base 4 of 10. So isn't my true statement x squared minus 6 must equal 10? Because there's no x, we can add 6. So we have x squared equals 16. Therefore, x must equal plus or minus 4. Now, I want you to think about this. X equals 4 and x equals negative 4 are our two solutions. Now, here is what's interesting, though. If you think about it, I'm going to go back to the picture of the graph of my logarithmic function. Look at the x values it can be. 1, 2, 3, all is good. But will our logarithm ever have a negative x value? No, look, it's rounding out in a 0. It's not ever going to be a negative inside a logarithm. It can't be because we have an asymptote, but I'm going to go back and not be mistaken because secretly, is that negative 4 even going to be a negative anymore when I plug it back in? No. So it's not a negative in there anymore because negative 4 squared is 16. 16 minus 6 is 10. Do you see how it's positive? So we're good. Does that make sense? So it's only if it makes it negative inside. So I want to scroll back up. So my example here, I just noticed for the first time, is yikes. It's not even true. Because can I have a negative 1 right there? No, so that wasn't a very good example, but you got the picture. That's what I was trying to go for. Sweet. Okay, ready? Show me you guys understand. Write the log as an exponential and the exponential as a log. Sweet, you went like this? Base 3, base 3. Therefore, 81 must equal base 3 to the 4th power, which is a true statement. I know I've done it right. Over here, you said I need to undo base 8, log base 8, log base 8. So 2 equals log to the base 8 of 64. Awesome! Okay, do 1 through 29 odds. We're not done with the lesson, but I'm going to give you time to now practice that before we move on. Home and they can't graph a logarithm without having issues, so you should take a few notes here if you need to. So really, how we graph logarithms is we just think about, we graph and we find the points of the exponential function and then switch them. So let's just look at this. If we were to graph 3 raised to the x power, we know we would have an asymptote at 0 here, and then we would plug in points. So just think in your head, if I plug in negative 2, don't I get a ninth? Everybody? If I plug in negative 1, I get a third. If I plug in 0, I get 1. If I plug in 1, I get 3. Jonathan, Johnny Cakes. If I plug in 2, I get 9. Okay. So now I'm going to draw that in. Okay, awesome. Now, so then, what's my domain of the exponential? Not the trick question. What's the domain? All real numbers. What's my range? 0 to infinity. Now, isn't, so, and my horizontal asymptote we said was at y equals 0. You're right. Okay, so then that will help us graph log to the base 3 of x, right? Because if you think about it, this is switch x and y. Y is equal to base 3 to the y, and then we take log to the base 3. Do you see what I'm saying? So now we would switch it, and then we have our inverse, log to the base 3 of x. So now we would just switch those points. So look, think about it. Over negative 2 up a ninth. So we'd go over a ninth down 2. Negative 1 up a third, so we'll go over a third down 1. Over 0 up 1, over 1 up 0. I should have drawn in my asymptote first, to be honest. Then over 1 up 3, so over 3 up 1. Over 2 up 9, so over 9 up 2 units. And now I can draw that in. So look how cool, because we know, since we know this, we know the domain of our original. What's the range of our inverse? All real numbers. Or we could look at the graph, right? But we just know we can switch our domain and range. So then the domain of our logarithm will be the range on our original, 0 to infinity. If you look at the graph, it does check out. So our vertical asymptote was at x equals 0. Okay, awesome. So that's going to help us graph a shifted logarithm. Everybody, this is where people have the hardest time. So listen to the steps you'll take to graph a shifted logarithm. Even after I taught this last hour, when people got to the book, they're like, wait, I don't know how to do this. So listen, if you need to take some notes too. To graph a shifted logarithm, you're not allowed to just type it into your calculator because first of all, it's base 3, but just you're not allowed. This is the work you would show. You should say to yourself, okay, let's look at the non-shifted function log to the base 3 of x, and then we'll take and add, shift our points, right? That's what we've done all year when we had shifted functions. To get these points, I would say, instead of looking at log to the base 3 of x, I'm going to look at base 3 to the x. Figure out those points, and then won't I just switch them to get my log points? We just did this, didn't we? Are you confused? Oh, it wasn't even about math? No, it wasn't. Can you ask me? I'm that mean and scary you don't dare ask? Yep. That's it. Get out! Okay. All right. So let's graph this. Do you see what I'm saying? I've already plotted these points. You see what I'm saying? Okay, cool. We switch them. So I'm going over a ninth down 2, over a third down 1, over 1 up 0. Why am I graphing these? We need to shift it, don't we? Yeah. Erasing. You're distracting me since you guys are all being so dang quiet. Just kidding. Okay, so I'll just blame you guys. Okay. So now what we have is our parent function points. Now in words we'll go like this. Left 1, up 2, right? So now instead of having the horizontal asymptote at 0, didn't we just shift left 1? That's where you would start. You would draw in your new asymptote that's been shifted, whatever unit left or right. All right, now let's find our new xy points. So if we went left 1, we took our x points, and won't we be subtracting 1? That's how shifting of functions work. And then we're going up 2. That would shift our y values up 2. So you would go off to the side. You would make a new xy chart. And you would tell me what the new points are going to be. So everybody take your calculator. Let's just do decimals. 1/9 minus 1 is negative 0.8. And then negative 2 plus 2 is 0. Yep. Yep, 1/3 minus 1 is negative 0.6. And then what's negative 1 plus 2? 1. Is everybody with me? Then over 1 minus 1 is 0. Then 0 plus 2 would be 2. Okay, 3 minus 1, 2. And then 1 plus 2 is, and then 9 minus 1 is, and then 2 plus 2 is 4. So now I can graph these points. I'm going back 0.8 up 0. I'm going back 0.6 up 1 unit. Over 0 up 2 units. Over 2 up 3 units. Over 8 up 4 units. And now because I know how asymptotes work, we know it's coming down like this. So what were the steps I did? Instead, I wrote it as an exponential, the parent function. I switched it to get my parent function logarithmic in logarithmic form, and then I performed the shifts to my xy points. Are you going to be able to do that when you get home by yourself? Sweet. Okay, so a couple last things here, and then we'll finish up, and you're going to have about 30 minutes in class to do as much homework as possible. So everybody, last couple of things. We already learned that log with no base written there, a blank base, is actually secretly base 10. Now here's something interesting and new. We know E is just approximately 2.7. We've been seeing like log to the base 5s, log to the base, well, I don't know, 3s. So this isn't that weird to have a log to the base E, because E is just 2.7. That's essentially having this, pretty much. Log to the base 2.7. But we're going to use E because E is exact. 2.7 is rounded. Now, this is actually how they write log to the base E. It's a special logarithm. Log to the base E, instead of writing log to the base E, they'll write ln, because that stands for natural logarithm. So that's just how they write log to the base E. Instead, they'll write ln, and that just means, like, ln is the same thing as a logarithm. It's a special logarithm. So properties of logs will hold true for LNs, for natural logs. So this is, guys, this is true, isn't it? Isn't this, if this is ln, wouldn't we undo log the base e with base e? Yeah. So what undoes ln? E, right? Because they're equal. ln and e undo each other. They're inverses. So let's do this. Simplify using properties of logs. E raised to the ln of 5 will be 5, because ln and e undo each other. They're inverses. 2 ln of e is 2, because isn't this 1? Undoes each other. Okay, ln and e undo each other, so this would simplify to be 2. E raised to the ln of 12 would be 12, because ln and e undo each other. You're awesome. Hey, what do you think this one's going to be? Let's see if there's any advanced thinkers. Thanks. Who said that? Who said -1? Woo! Look how smart you are. Yes. Yeah, this is the same thing as ln of e to the -1, isn't it? This? So then don't they undo each other? -1. Awesome. Now, if this tricks people, we've got to be careful because there is a difference between this. There's a difference between ln of 1/3, and then this one is not ln of 1/3. This one's ln of 1 over 3. Can anyone tell me what this one? Who's an advanced thinker? Don't use a calculator, Jonathan. Just kidding. I know you were just texting. What's the answer? There's some smart people in this class. You're all smart. Yeah. 0. Look at that middle group. They're awesome. It's 0. Remember, didn't we learn that log to any base of 1 is 0 every time? So this is log the base e of 1, which would be 0. So this is 0 divided by 3, which equals 0. So ln of 1 is 0, everybody. Sweet. Okay, just a little quick note. You don't need to take notes here. Just look. Graphing e. Okay, so looking at this, graphing e to the x, we did that last time. We know that that's just a bunch of decimals, right? We could graph it. So if we wanted to graph ln, since that's the inverse, we would just switch these xy points and graph it so it would look like this. Is everybody good with that? Awesome. Okay, what I want you to do is prove to me you were listening. I want everybody to do it, including you, Johnny. Okay, do these two problems. So rewrite this as an exponential and rewrite this as a logarithm, as an ln. So how do we undo ln? E both sides. So then we would have 2/5 is equal to e raised to the -0.916. Thank you. And I promise you that is true. You could type it into your calculator. Type in e raised to that, and you would get the same as 2 divided by 5. So we've just rewritten it in exponential form. So let's rewrite this one. We would do the ln of both sides. So then 2 equals ln of 7.389. And you could type that one into your calculator because there is an ln button, and you would see it really is a true statement. Cool, that is the end of the lesson. So get out your little white paper and do the problems that are assigned.